Hi everyone, welcome back to MATA35. There appears to be a typo. This is actually lecture 11A, not 10D. So notably, this means that the material on today's lecture will not be assessed on quiz 5. However, a lot of it is related to quiz 5 because it's the nonlinear version of the stuff that we're doing. So I'm going to go ahead and get started by just re-summarizing all the material from lecture 10C and 10B. Because this is really important information. So, if you have a linear system, x dot y dot is equal to a matrix a, b, c, d times x, y, where A is this matrix, the origin is always an equilibrium point. What this means is that if you apply x dot of 0, y dot of what this means is that if you're applying this, A, B, C, D, you plug this in, you plug in the origin point, that's always equal to itself. And so therefore, this is an equilibrium point. Oh, sorry. I am messing things up. But in this particular case, it is always an equilibrium point because what this means is that it is not going to change at all because x dot y dot, the amount that it's changing the y-axis or the x-axis or the y-axis for the origin point is always going to be equal to 0. So now this is an equilibrium point, and we want to understand the behavior of the system around the equilibrium point. And so there are a couple ways of doing this, and we just have to look at the eigenvalues. Positive real parts say that the trajectories go outward. Negative real parts mean that the trajectories go inward. Opposite sign eigenvalues mean that you have a saddle point. So now when the trajectories go outward, you have an unstable equilibrium. When all the trajectories go inward, you have an asymptotically stable equilibrium. And when some go inward and some go outward, that is still unstable because you have trajectories that go outward. Next, we also have real versus complex eigenvalues. Real eigenvalues result in either nodes if both of the eigenvalues are the same sign, or saddle points if they're different signs. Non-zero imaginary components mean that the trajectories spiral. And if you have pure imaginary eigenvalues, they give rise to a center, which is stable. Okay, so this is our review from lecture 10C. And last time, we talked about the stability of a bunch of different possible groups of eigenvalues. This time, we're going to talk about classifying by the type of behavior. So I'm going to ask, are these nodes, saddle points, spirals, centers, or none of the above? So we're just going to go through the same examples again. So if one of your eigenvalues is 4 and the other is -2, what sort of behavior is this? Okay, yes, exactly. So this is a saddle point because, you have different saddle point, B, saddle point, different signs. Okay, let's keep on going through this. Let's try another one. Let me reset quickly. So if you have two negative eigenvalues, what do you have? Yeah, so they're both real, and importantly, they have the same sign, and therefore you have a node. Let's go on to the next one. Let me reset. So if you have two eigenvalues, both of them positive, what kind of classification do you get? So remember, the questions are the eigenvalues real, and are they the same sign? Yeah, exactly. So this is still a node. Let me try, let's reset and do yet another one. What about if both of the eigenvalues are equal to 3? So don't overthink this too much. Yeah, exactly. So this is still a node. This is still a node, but it might be proper or improper. Be proper or improper, depending on the eigenvectors. Okay, so those are all pretty straightforward. Let's try some slightly more interesting ones. So what about 3 plus or minus 2i? Yeah, so this is complex, and it has a non-zero real components, and so therefore this is a spiral. And let's do one last couple more. So we have -1 plus or minus 2i. So again, the question is it complex? And if it's complex, then yeah, it is indeed a spiral. And for the very last one, you guys should know what's coming since we covered these same examples last time. So what about if you have plus or minus 4i, where the real part is equal to 0? Yep, exactly. So this is a center. And note that weird stuff can happen when your eigenvalue is just equal to 0. We're not going to deal with that. That's a very rare case anyway. But weird stuff that happens when the eigenvalues can happen if the eigenvalues are equal to 0. Okay, so let's see a couple examples of this. So this is all linear stuff. So these are, if you're wondering about whether this will appear on quiz 5, this is all material that can still appear on quiz 5 since we're still in the linear regime. This is all just a review of the last lecture. So let's classify the behavior of the origin, or as an equilibrium around the behavior around the origin of the system, where you have the matrix A is equal to 1, 3, 3, 1. So what we have to do is, the first thing is we have to compute the eigenvalues. So in order to do that, lambda minus 1, minus 3, lambda minus 1, take that determinant, set it equal to 0. So that's lambda squared minus 2 lambda plus 1 minus 9 is equal to 0. And so you're left with, let's see, what would this be? Lambda squared minus 2 lambda plus 8, minus 8, sorry. Minus 8 is equal to 0. Which implies that lambda minus 4, lambda plus 2 is equal to 0, and so lambda is equal to minus 2 or 4, and so therefore we have a saddle point. And let's do another one, just so that we, again, all we have to do here is we have to compute the eigenvalues. And so it's going to be lambda minus 1, minus 3, 0, lambda minus 1. It's going to be equal to lambda minus 1 squared is equal to 0. So lambda is equal to 1 with multiplicity 2. So now, that by itself is enough to tell you that this is a unstable node. Right? But now, sometimes I might ask you to classify even further. So if I want to ask you, is it proper or improper, then you need to check the number of eigenvalues. So to determine if improper or proper, check number of eigenvectors. And so when we do that, what we do is we take 1, 3, 0, 1 times xy. The eigenvalue is just 1, so that's equal to xy, which implies that x plus 3y is equal to x, which implies that y is equal to 0, which implies that v1 is equal to 1, 0. So you only have one eigenvector, so only one eigenvector. So improper node. Okay, so this was the other more subtle part of the classification. If you only have one eigenvector, then you will, for an eigenvalue of multiplicity 2, then that will be an improper node. And these are really hard to graph out, and they won't show up that often, but just be aware of it. Okay, so let's have you all try it out with actual matrices. Let me reset. I want you to classify the behavior around the origin of x dot y dot is equal to 1, 3, minus 3, 1, xy. So the first question is it asymptotically stable, stable, unstable, or none of the above? So remember, what you have to do is the first step is always just to compute the eigenvalues. You want to set that equal to 0. So can there be different eigenvectors for the same eigenvalue? Yes, there can. So the only time that will happen, is that true? So in general, the only time that will happen for the types of problems that you guys will be seeing will be when you have a diagonal matrix. And note that if you have different eigenvalues, then of course you have different eigenvectors. So an eigenvector cannot be the eigenvector for multiple eigenvalues. Okay, but so in this problem, we're trying to figure out what the eigenvalues of this are so we can classify its stability, right? Okay, it looks like people are starting to give responses. Hopefully everyone's not just jumping on the bandwagon, but in this case, it is correct. It is unstable. And so the way you can see this is if you write this out, this is, let me solve this by completing the square, since it'll actually be slightly easier. So lambda minus 1 squared plus 9 is equal to 0. And so you have lambda minus 1 squared equals minus 9. Lambda minus 1 is equal to plus or minus 3i. And so lambda is equal to 1 plus or minus 3i. And so your answer is that this is actually unstable. Okay, let me reset quickly and then ask my next question, which is, what kind of behavior is this? Is this a node? Is it a saddle point? Is it a spiral, a center, or none of the above? So now that should be pretty obvious from the eigenvalues, because here, we have complex eigenvalues, and therefore this is a spiral. Okay, so hopefully this was helpful in just practicing some of the concepts we learned in Lecture 10C. And I will just mention that this is the point at which the material that may show up on Quiz 5 completely properly ends, because next we're going to be talking about nonlinear autonomous systems and Jacobians. So earlier we had this example where x dot y dot was equal to some matrix times xy. But we also saw that we could have nonlinear systems where x dot is just equal to some function of x and y, and y dot is equal to just some function of x and y. And then you're left with, and then you have equilibrium points whenever x dot is equal to 0 and y dot is equal to 0. So let's give a quick example. Let's say we had the system x dot is equal to x squared plus y squared minus 1, and y dot is equal to 2xy. So this is clearly nonlinear. In order to find the equilibrium points, well, you have to set both of these equal to 0. So 0 is equal to x squared plus y squared minus 1, and 0 is equal to 2xy. Well, we know from 2xy that that implies that either x is equal to 0 or y is equal to 0. If x is equal to 0, then we plug that back into the first equation and get y is equal to plus or minus 1. And if y is equal to 0, then x is equal to plus or minus 1. And so therefore you get 4 equilibria, which are the points 0, 1, 0, minus 1, 1, 0, and minus 1, 0. Does that make sense to everyone? So equilibrium points are whenever both x dot and y dot are equal to 0. In the previous example of a linear system, that was easy because you could just set x and y both equal to 0 and you get an equilibrium point. And that's why the origin was always an equilibrium for a linear system. For a nonlinear system, that's not the case. So for example, for this nonlinear system, 0, 0 isn't an equilibrium because x dot would then be equal to minus 1. But instead we have these 4 different equilibria, and we'd like to understand the behavior, and the equilibrium point is just the point at which the trajectories don't go anywhere, so they stay in place. But if you go slightly away from it, if it's unstable, it might run away. But now the question is, what is the behavior around each of these equilibrium points? Now, if you think back to when we talked about multivariable calculus, you might remember that we can approximate a function around a point using its derivative at that point, right? So for example, if you have some function that looks like this, well, you can approximate the function around the point here by just looking at the tangent line. And if you're close enough to the tangent line, then that is a good approximation of the function. So now, what is the derivative of a multivariable multi-output function? So you can think of this as a function that goes from r squared, from a point in the xy point plane, to r squared, a direction in the xy plane. And so this is a function from the plane to the plane in some sense, or at least the direction on the plane. And it turns out that the derivative of this kind of multivariable function is something called the Jacobian matrix. And so since this is a function from R2 to R2, this is a 2 by 2 matrix where the top row is the gradient of the f function and the bottom row is the gradient of the g function. So top row, so now we have to remember back to our partial derivatives. So top row is the partial derivatives of f with respect to x and y, and the bottom row is the partial derivatives of g with respect to x and y. So what is the Jacobian here? The Jacobian, well, j of xy is going to be equal to, well, what's the top row? That's the partial f partial x, so that's 2x, 2y, and the bottom row here is, well, 2y, 2x. Okay, so now we have the Jacobian matrix. We can understand the behavior around each of the equilibria by just looking at this Jacobian matrix for that particular point. And we can approximate the behavior by looking at this matrix's eigenvalues. So let's make that a bit more concrete. So we have the Jacobian matrix, j of xy is equal to 2x, 2y, 2y, 2x. And now this has variables in it, but what we can do is, if we look at the first equilibrium, which was 0, 1, we can plug that into this Jacobian matrix. You're left with 0, 2, 2, 0. And when you do that, you can look at the eigenvalues of this matrix. If you look at the eigenvalues of this matrix, lambda minus 2 lambda is equal to 0, which implies that lambda squared minus 4 is equal to 0, so lambda is equal to plus or minus 2. Okay, so what this is saying is that the behavior of the system around the point 0, 1 is actually a saddle point, because you have these two different eigenvalues, saddle point. And furthermore, if you want to know what direction it goes in on and what direction it goes out on, you can again look at the eigenvectors. So lambda 1 is equal to 2. It turns out that v1 is going to be equal to 1, 1. So you can compute this by just computing eigenvectors. I'm not going to do it right now. Lambda 2 minus 2, v2 is going to be equal to 1 minus 1. So what we're saying is, actually let me write this on the next slide, since we can get a local phase portrait around the point 0, 1. We have lambda 1 is equal to 2, and v1 is equal to 1, 1. Lambda 2 is equal to minus 2, and v2 is equal to 1 minus 1. And so that means we have some equilibrium point. This is the point 0, 1. So if you think about this, you can think about this as being on the point 0, 1. So that is 1. So we have some point 0, 1 there. And what we're going to say is that we have these two eigenvectors. So one of them is in this direction, and the other is in this direction. And the eigenvector, that's 1, 1, has a positive eigenvalue, so it goes out along that eigenvector. And the other eigenvector has a negative eigenvalue, and so it goes inward along that eigenvector. And the behavior around this point is going to look like this. Now, we don't know what happens off here in the distance, like it could go anyway. But we know that close to the equilibrium point, it's going to have a saddle point behavior, because we just looked at the Jacobian matrix at that point. And we can do this for all the various points, all the various equilibrium points. So that was the equilibrium point 0, 1. What about the equilibrium point 0, minus 1, which was one of the other equilibria that we computed on the previous slide? So in order to do that, we take a look at this matrix. So that's when we plug in minus 1 for y and 0 for x, we get 0 minus 2 minus 2, 0. And so that's going to be lambda 2, 2 lambda is equal to 0. You again get lambda squared minus 4 is equal to 0. Lambda is equal to plus or minus 2. And we get another saddle point. It turns out that for lambda 1 equals 2, the eigenvector here, which I'm not going to compute, but you guys know how to do that by now, is going to be 1 minus 1. And the other eigenvector, minus 2, is going to be equal to 1, 1. And we can draw that out. So if we go back onto this other slide, and we have 0, minus 1 as our equilibrium, we have lambda 1 is equal to 2, lambda 2 is equal to minus 2, v1 is equal to 1 minus 1, 1 minus 1, v2 is equal to 1, 1. And so Note that here, if you look on the plane, this is 0, -1, so that's this point here. And our eigenvectors still go in we have the 1, 1 direction, so we have an eigenvector going this direction, another eigenvector going this direction. But now on this one, the eigenvector 1, 1 has a negative eigenvalue, so that goes inward, and the other one goes outward. And so this is a saddle point that goes in the opposite direction of the previous one. So again, this doesn't tell us what happens around here. But of course, we already know what happens around there, because that's precisely the behavior of listing here. So what we're doing is we're finding local behavior around each of the equilibrium points. And we have two other equilibrium points, so let's walk through those. These are a little bit easier, because if you have a Jacobian for 1, 0, that's just equal to 2, 0, 0, 2. Did I do that right? Yes, 2, 0, 0, 2. And so then lambda is going to be equal to 2 with multiplicity 2. It turns out that there are eigenvectors here. This has two eigenvectors because it's diagonal. You can just get 1, 0 and 0, 1, but it doesn't really matter because this has two eigenvectors, so this is a proper node, and so this is an unstable proper node. And we can also do the same thing for -1, 0, and that's left with -2, 0, 0, -2. This is diagonal, and therefore your eigenvalues are -2 with multiplicity 2. And it is again it is a stable proper node. Stable proper node with the same eigenvectors. So what does that look like? Well, if we have 1, 0 as our equilibrium point, we have lambda is equal to 2 with multiplicity 2, and we know it's a proper node, and so it's star-shaped. And when we draw this out, 1, 0, that's going to be a point here. And all the trajectories are going to go out in every direction. So this is unstable, so you just have a star, and trajectories all go outward. And lastly, we have the other equilibrium for -1, 0. Lambda is equal to -2 multiplicity 2. This is also a proper node. And when we draw this out, you have this point here, and all the trajectories go inward. Okay, and you'll notice that we have all these various local pictures at different points around, and we can put them all into a single portrait. And so that is an actual phase portrait for this nonlinear system. So when we draw that, well, let's go ahead and draw this entire thing. We have 4 different equilibrium points. They're here, 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 and here. And for the ones on the y-axis, those, we had these two eigenvectors for both of them, except one of them went in on the down diagonal and out on the up diagonal, and the other one went the other way. And we know that these just go out in every direction. Or sorry, yeah, that one goes out in every direction, this one goes in every direction. And so we have all these local pictures, and what this gives us is this gives us a global view of how the system behaves. Because things are going to go out, they're going to go in that direction, they're going to go here, and so on. And so this allows us to get a qualitative view of the entire phase portrait for a nonlinear system of ODEs. And if we plot this out in something like Wolfram Alpha, we end up getting something like this picture. So you note that our equilibrium points here were layer, 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 and layer. And so even without plotting this out by hand, we were able to get something, or by just looking at the equilibria points, we were able to get something that approximated the entire phase portrait and all these integral curves, while by just looking at the eigenvalues of the Jacobian matrices. Okay, and the basic idea is that around each equilibrium point, you can linearize it by just looking at the Jacobian, and then the behavior is as if it were linear with that matrix and that set of eigenvalues. Let's have you all try it out. Hopefully you guys are still awake. So let's go on to the next slide. So I chose a relatively simple system, and I'm going to ask you a series of questions. So the first one is, let's talk about what the equilibrium points are for this nonlinear system. So I've given a couple of choices here. Remember, an equilibrium point is when both the x dot and y dot are equal to 0. So which of these are equilibrium points for this nonlinear system? Okay, it looks like we have a lot of responses for A, and that is indeed correct. So what we're doing is xy is equal to 0, and 0 is equal to x plus 2y minus 8. Well, case 1, x is equal to 0. If x is equal to 0, you plug that in, and so you get 0 is equal to 2y minus 8, and so therefore y is equal to 4, and so one of our points is 0, 4. Case 2, we have y is equal to 0, and so then we're left with 0 is equal to x minus 8, which means x is equal to 8, and you get 8, 0. So the answer is indeed A. Okay, so now we have the equilibrium points. We need to find the next thing we need to do is we need to find the Jacobian matrix. We need to turn it into a linear system because then we can use the eigenvalues. So let's find the Jacobian matrix for this nonlinear system. And let me reset. Okay, and just remember, before responding, that j of xy is going to be equal to the partial x derivative of the top equation, the partial y derivative with respect to the top equation, partial x derivative with respect to x plus 2y minus 8, and partial y derivative with respect to x plus 2y minus 8. And it looks like everyone has decided that this is D. Well, when we write this out, this is indeed equal to y, x, 1, 2. And so the answer is indeed D. Okay, so now what we've done is we've almost turned this into a linear system. For any point in the xy plane, if you plug that into the Jacobian, you'll know what the linear approximation around that point is. Now, of course, we mostly care about this for the equilibrium points. So let's use the Jacobian to determine the behavior around the first equilibrium point. So the questions are, is it asymptotically stable, stable, or unstable? And in a moment, I'll ask you to classify it, of course. Let's see, did my reset take? Oh, it just took a moment to update. Okay. So, I should go ahead and let's copy down the equilibrium point. xy is equal to y, x, 1, 2. And our first equilibrium point was 0, 4. That's equal to 4, 0, 1, 2. Okay, it looks like everyone is basically done. And people are saying C, it is unstable. Well, this is a triangular matrix, and so therefore lambda 1 is equal to 4, lambda 2 is equal to 2, and yes, this is indeed unstable because both of the eigenvalues are positive. What about, is it a node, a saddle point, a spiral, or a center? Okay, yeah, so both of the eigenvalues are the same sign and they're real. And so therefore, this is a node. And so this is you're going to have, meaning that the local picture around here is this is 0, 4, 1, 2, 3, 4, and it's going to be unstable, so everything's going to go out of it. Now, if you wanted to, you could compute the eigenvectors, and then that would tell you what directions it goes out. But for now, if I ask you to do this in practice, I will accept if you just say all the trajectories go outward, and you don't have to actually compute all the eigenvectors to figure out which direction it goes out faster. for the nodes. You will still have to do that for the saddle points, though. Okay, let's go on to the other equilibrium. So we have another equilibrium. So around the second equilibrium point, which is 8, 0. I'm going to ask you the same thing. Is this asymptotically stable, stable, unstable, or etc.? Let me reset the chat. And so what we have is we have the Jacobian matrix xy is equal to yx12. We're going to plug in 8, 0, j of 8, 0. So that's going to be 0, 8, 1, 2. And the question is, what are the eigenvalues, and does that mean that this is stable or unstable? Oh, it looks like many people are already done. And, oh, okay, so we have a very high quorum for unstable. Well, let's take a look at what happens. So if you compute the eigenvalues, you get lambda minus 8, minus 1, lambda minus 2. That's equal to lambda squared minus 2 lambda minus 8, which is equal to 0. You get lambda plus 2, lambda minus 4 is equal to 0, lambda 1 is equal to minus 2, lambda 2 is equal to 4. And since this is indeed unstable, because you have a positive eigenvalue here. The next question is, of course, well, what kind of behavior is it? Okay, that was a really quick answer. So yes, exactly. So because we have one positive eigenvalue and one negative eigenvalue, this is indeed a saddle point. Now, suppose I want to actually graph this out. That's a little bit more complicated because with the saddle point, you need to know which direction it goes in and which direction it goes out. So if I'm trying to graph this, well, this is some point that's sitting here, but I don't know which direction it goes in and which direction it goes out. And so in order to do that, I need to compute the eigenvectors. So if I have lambda 1 is equal to minus 2, when you plug that in, what you'll find is that 8y is equal to minus 2x. And so the first eigenvector is minus 4, 1. The second eigenvector, for the eigenvalue 4, is going to be 8y is equal to 4x. So v2 is going to be equal to 2, 1. And so we have a couple different directions. So one direction, the first direction here is this direction. It's going to be minus 4, 1. So in the x direction it goes minus 4, so, and the other direction goes 1. So that's this eigenvector. So it goes in that direction. The other eigenvector, 2, 1. So what we're saying is that, oh, I messed that up, didn't I? I definitely messed it up. Let me draw that again. So we have this point here. The eigenvector, it's minus 4, 1. So it goes up 1, and then it goes minus 4. So that's this direction, actually. The other eigenvector goes up 2, and then goes to the right 2 and goes up 1. So that's here. And so this is this eigenvector. And along that eigenvector, it goes outward. And on the other eigenvector, it goes inward, because those are because of whether the eigenvalues are positive or negative. And so then they are left with trajectories that look like that. The next thing we want to do, of course, is we want to put it all together and to draw a full phase portrait. So we have the two different equilibrium points. We have 8, 0 and 0, 4. We know that around this equilibrium point, everything goes outward. On this equilibrium point, we have these two directions. And things go, what was it? Inward in that one? Yeah, inward in this direction and outward in this direction. And so if you want to draw out some potential solutions or trajectories, you might have something that goes like that. Or something that goes like that. And when we plot this out on the computer, that is indeed what we get. So it's a little bit harder to see, but we have our x-axis here and our y-axis here. And our two different equilibrium points. One of them is here, and you can sort of see it going in and out. And our other equilibrium point is here, and everything goes out. Okay, so basically you can use linearization by using these Jacobian matrices, and then you can use all techniques we learned for Quiz 5 in terms of these eigenvalues of the matrix. Now, you guys now have all the tools you need in order to actually model biological systems. So, let's do that. So we're finally getting back to biology, and and other than the linearization stuff, we're going to see some examples now that you guys finally have all the tools you need. So, wolves and deer. This is a classic example of predator-prey relationships in an environment. So, consider an environment with wolves and deer. And you have some population of deer, let's call it X of t. You have some population of wolves, let's call it Y of t. And the two are related to each other, obviously, because the deer eat the wolves. And so if you have lots of deer, well, then the wolf population can get bigger. But when you have lots of deer and then you have lots of wolves, well, the deer population gets smaller because the deers are being eaten by the wolves. So let's model this. So one way of modeling this is to say the deer grow exponentially, but the population is kept in check by predation from the deer. So here, what we're saying is this here is the exponential growth for the exponential growth for the deer. So with that, if there weren't any wolves at all, the deer would just grow exponentially. Now, this isn't a great model necessarily because, as we know, like things can't grow exponentially forever. Eventually, it'll hit some limit. But it turns out that in this simple model with both wolves and deer, the deer are able to are kept in check by the wolves. So this here is an interaction term, because it turns out that deers and wolves interacting tends to be a little bit bad for the deer. So interactions between the two, which are modeled by this xy term, since you have a combination of both the wolves and the deer, interactions are bad for the deer and cause the population to get smaller. Now, the wolves are also trying to grow, but they'll die out unless they can find enough deer to eat. So then there's this very simple model, the wolves only eat deer. So you have a dying out term here. So wolves are just naturally dying out unless they can find enough deer to eat. So interactions are good for the wolves. Okay, and this is a very simple predator-prey model where the deer are the prey animal is just growing exponentially, but then they get eaten up by the predators. Okay, so we have a system of equations. Now we're back in math land, and we can try to interpret what happens to these wolves and deer. And for this particular model, a really interesting thing actually happens, which we'll see in a moment. But the first thing we need to do is we need to find the equilibrium points, right? So in order to find the equilibrium, 0 is equal to 2x minus xy is equal to x times 2 minus y, which implies that x is equal to 0 or y is equal to 2. We have our other equation, which is 0 is equal to minus y plus 0.4xy, which is equal to y times 0.4x minus 1. So you have a couple different cases. Case 1, x is equal to 0. Well, if x is equal to 0, then y is equal to 0. And so one of our equilibrium points is 0, 0. This makes sense, right? Because one equilibrium of the system is therefore there to be 0 wolves and 0 deer. That is obviously an equilibrium. If you don't have any deer or wolves to begin with, well, that will never change. And so it's a steady state. The other case is a little bit more interesting. So case 2 is going to be the case where y is equal to 2. And it turns out that when you solve this, you get 0 is equal to 0.4x minus 1, which implies x is equal to 2.5. So you have this other equilibrium point where you have 2.5 deer. I mean, these numbers are all dimensionless. So you have some amount of deer and some amount of wolves, and there is an equilibrium. Now the question is this a stable equilibrium? And, well, in order to figure that out, we just need to take the Jacobian matrix. And so the Jacobian matrix here is equal to 2 minus y minus x, 0.4y minus 1 plus 0.4x. And so we can actually compute the stability. So every ratio of 2.52 is an equilibrium. No, that's a very good question. That's not quite right. So you should think of this as a dimensionless thing. So it's not the ratio that's an equilibrium, it's the exact value. Of course, one way of thinking about this is maybe it's 2.5 times 1,000. The equation has Yeah, so you have some unit here, and the unit might be thousands of deer. One of the issues with doing this sort of mathematical modeling is, of course, there are still some non-physical things. Like, you can't actually have a fractional number of deer, but mathematically, well, there's nothing to keep you from having a fractional number of deer. But just think of this as 2.5 times 1,000. Okay, but now let's figure out the stability of each of these two equilibria. So we have j of 0, 0 is going to be equal to 2, 0, 0 minus 1. And so this is diagonal, so the eigenvalues are just on the are just the diagonal of entries there. So lambda 1 is equal to 2, lambda 2 is equal to minus 1, and v1 is going to be equal to 1, 0, and v2 is equal to 0, 1. And this is, of course, a saddle point, and so it's unstable. So it turns out that this is unstable, and one way of thinking about it is, well, if you even go slightly off of the 0, 0 point, if you just introduce, say, 2 deer into the environment, then all of a sudden, well, they can exponentially reproduce. And once you have deer in the environment, you can, in theory, have wolves. Though, of course, you have to be a little bit careful not to end up with negative numbers. But once you introduce wolves and deer into the environment, well, they're not going to go extinct in this model. And let's take a look at j of 2.52. So this is the other equilibrium point. You get 0 minus 2.5, 0 0.8, and 0. And so if you actually solve this out, I'm not going to go through the full process, but you end up getting lambda squared plus 2 is equal to 0, and lambda is equal to plus or minus I times the square root of 2. So this is actually a center, which is a little bit weird, right? Because this is pure imaginary. So what we're saying here is that around this point you have lots of circling trajectories. So let's try drawing this out and understanding what's going on here. So we have, let's plot this out. We have deer here on the x-axis and wolves here on the y-axis. Well, one of our equilibrium points, this point, is really easy to understand because we have two different eigenvectors, and along one of the eigenvectors it goes in, and on the other it goes out. And you're left with, and we also have this other equilibrium point here. So this is 2.52, and this is a center, which means that in theory, trajectories are going around it. We don't know exactly how big these trajectories are. We just know they're circling it in some way or another. And so what we're left with is something like this. And of course, we have other stuff going on here in the other quadrants. But it's important to remember that this is all not physical because you can't have negative numbers of wolves or deer. And so what you're left with is a phase diagram where things seem to be going around in circles. So, for example, if you're following along one of these solutions, let's say you start, let's choose a different color. Let's say you start here. You have some amount of deer and some amount of wolves, but you have too many wolves, and so it's causing the number of deer to decrease. So it's going along here, and the number of deer is decreasing because the wolves are eating them. And then they overeat the population, and there are so few deer that the wolves start dying out as well. So the wolves start dying out as you keep on going along here. But then once enough wolves die out, then, well, the deer population can rebound because there aren't enough, they aren't getting all eaten up anymore. And so the deer population gets bigger, but then of course once the deer population gets bigger, the wolf population can get bigger as well. And so you end up with these sorts of cycles, which is one of the interesting things about wolf and deer populations, is they do tend to be a bit cyclic. So there is this boom and bust of the number of wolves and deer. And we can see this when we plot out the phase diagram. So of course, all this stuff doesn't matter because this is not physical. And you end up with these cycles of numbers of deer and wolves just cycling around. So sometimes there are more wolves, sometimes there are more deer, and sometimes the deer eat not the deer eat the wolves. The wolves eat the deer, and therefore the number of wolves goes up and the number of deer goes down. Deer goes down, and this cycle keeps on repeating. And I think that's basically the end of today's lecture. I'm just giving you a taste of the sort of things that you guys are now equipped to do. You guys have all the tools you need now to understand some of these biological systems using the techniques that we've been discussing. So and this really does combine together a lot of stuff that we've been learning throughout the entire class. So this combines together some of the linear algebra stuff because we're taking eigenvalues of these Jacobian matrices, combines together multivariable calculus since you're taking these higher order derivatives to get these Jacobian matrices, and then we have all these ordinary differential equation solutions, and we can analyze them qualitatively by just looking at the amount of the deer and wolves going around in the circle. Any questions? Okay, well, given that, I'm going to stop the recording, and that is the end of today's class, and I will stick around for office hours.